AIST Japan, classification and key features of this constellation.
Thank you, Chairman. I'd like to thank the organizer for inviting me to this wonderful workshop. And first of all, I'd like to apologize because of the very bad jet lag. I was sick in the first day, so I missed almost half of the talks in this workshop. So in order to apologize and also compensate my talk, I changed my talk a little bit. At first, I'd like to show the very recent result of my investigation of the Memristors. That is okay. So that is actually stimulated by this interesting paper. I found this on the internet. This is an attractive title. You can see the speed of dissemination of the information about the realization of the force passive electronic circuit element measured by Google hits. So this is sorry. So this is the main result of that paper. They have counted the word Memristor hit in the Google research, and that increases rapidly as a function of time. This is a log scale, and reach to this amount, and decreases in this way. So that is interesting. So I like to do that kind of research by myself, but I don't have any friends in Google companies. But Google actually providing the function, so we can do that by ourselves. I didn't know that, but so I did that. This is a hit as a function of the time, 2008 and 2009. This is a word Memristor. So it reaches to the maximum. This is normalized to 100. Okay, so it decreases like this. And the interesting thing is the most important, the people who are most interested in the word Memristor is in India. I don't know how many Indians are here in this workshop, but the Indian people are most interested in the word Memristor. The United States, Canada, Germany, and Japan didn't place high in this round. So, unfortunately, I'm a Japanese, and Zimbabwe doesn't have any meaning because after 20% or something, it doesn't count. Okay. So I am also doing the research of Aram. So I checked the Aram, but it's almost nothing these days. So people are not interested in Aram nowadays, unfortunately. But still, the people in the United States are somehow interested in Aram. Again, in Japan didn't place high in this rank. So is this a correct ranking? So I checked another word that is HRP4C. Maybe you are not familiar with this word, but this word gave a great impact in Japanese among Japanese youths or nerds. You know, some Japanese geeks got so interested in this word because this is the human type android. Okay, so this one actually made in our institute at AIST, unfortunately or fortunately. So this made my institute very popular in Japan. So this and the number of the count is almost almost equal to the Memristors. So I realized number of the geeks who are using the Memristor and the HRP4C is almost similar. Okay, so I think Google is right. Okay, and also I mentioned another word, Ichiro, that is a baseball player, and you're not familiar, but he is very popular in the United States. He's a major league player, and also Japan and Taiwan people are interested in. So these three are almost in the equal level. So I realized Google is right. So this is not my conclusion of my talk. Okay, so I like to start my talk. Okay, maybe you're interested in the talk now. So, okay, I like to start my talk now. This is my mission is to classify all the key features and risks, and also the IV hysteresis of the response switching. My name is Isao Inoue. My institute is now familiar with that humanoid type android, AIST, and my research, but I'm not doing that kind of research, and I'm not such a person. Okay, anyway, okay, so. But I like to put that anyway. Okay, so you can see a lot of kinds of hysteresis in the sandwich structure of the oxide and metal electrodes. And sometimes the oxide is replaced by the organic materials, but I'm not quite sure whether actually the organic plays a role. So first of all, I like to say the hysteresis can be classified into two types. One is called the threshold type, and the other one is called the branch types. This and so even the same materials. This is an example of the strontium titanate. Okay, this is a polycrystalline strontium titanate, and this is a single crystalline strontium titanate. The electrode is platinum here, and the electrode is oxide, metallic oxide, strontium glutamate. But this interface is epitaxial interface, and this is okay. So just platinum is sputter, I think. So this is not the epitaxial interface, and so even the same material shows different types of hysteresis. This one is called threshold type, and this one is called branch type. Let's say. So, okay, let's see the branch type. Sometimes this branch type hysteresis is followed by the negative differential resistance. So this is a clear negative differential resistance. But most of the cases, you can see this kind of clear NDR. Okay. So in my talk, I like to say this kind of switching is also called NDR. Okay. So I like to call this type also NDR. Okay. And okay, back to the threshold type. So this one is very interesting because, for example, this one is we sweep the current. Okay? To sweep the current from the high resistance state and hit the point that is called set, then there is a sudden change of the resistance occurs here, and the system goes to the low resistance state. Okay? So this is an example of the nickel oxide. Okay, you see the clear change of the resistance here. But if instead of sweeping the current, you can sweep the voltage, then the oscillation starts here because this one doesn't have any counterpart here. You sweep the voltage here. It doesn't have any counterpart. I'm sorry, I couldn't put the example here, unfortunately. Okay, so, but this oscillation is quite hard, so the sample will be broken rapidly. So instead of to prevent the sample will be broken, we usually put the current compliance. Maybe you know very well. So this means we change from this point, the resistance state goes to this point. With the current compliance is this one. So instead of put the current compliance instrumentally, you can connect the serial resistance to the samples. That can avoid broken the samples. Okay. So this is an example. Okay. So for the reset switching, you can sweep the voltage here, and that shows again the clear change of the resistance at this point. And instead of sweeping the voltage, you can sweep the current again. The oscillation starts here because there's no counterpart here. So no state exists here. So you need to put another voltage compliance this time to avoid that kind of severe oscillation, and the sample is maintained. And then you can continue the sweeping like this. Okay? This means you reduce the switching from here to here. Okay? So, but this kind of threshold switching is quite different from the well-known threshold switching that I call it normal case. The threshold switching is realized usually in the spatio-temporal filamental formation. I mean the dynamical formation of the filament inside samples. So, have you ever heard the word S-type negative differential resistance or N-type negative differential resistance? That can be realized by the formation of the current filament for the S-type negative differential resistance and the voltage domains for the N-type negative differential resistance. So if you sweep the current, okay, and if the current filament is formed inside a sample dynamically, then you see the S-type negative differential resistance. But if you sweep the voltage for this type of materials, then you observe the threshold switching because there's no state over there. So it changes from here and comes back. So this is called a normal threshold switching. But our case, we actually observe threshold switching, but it's different here. So this is another one. This is N-type negative differential, so negative differential resistance, and threshold switching can be observed if you sweep the voltage, but if you sweep the current, you only observe if you sweep the voltage, you observe the N-type NDR, but if you sweep the current, you see the threshold. So, as I said, in most of the binary oxide materials, which show the threshold switching or the resistance switching, we can see the threshold switching for both the voltage sweeping and current sweeping measurement. So that is different from the dynamical formation of the filament inside. Okay, I'd like to say for this threshold type switching, this is not due to the dynamical spatio-temporal filament formation. And so what is the reason, what causes actually this one, this switching? I think this might be caused by the chemical reaction, or chemical phase transition. So this one is the this one is a rapid chemical reaction, and the branch type is caused by rather slow chemical reaction. So Okay, I'd like to explain what kind of chemical reaction from now on, but before going to the details, I'd like to say where actually the chemical reaction occurs. Okay. This was done by my colleagues, PhD colleagues. This guy is actually the researcher of the oxide fuel cells. So those people are quite familiar with that kind of chemical reactions. Okay, so they said the chemical reactions occurs usually at what they call the triple phase boundaries. Okay, so you see this is a cathode, this is metal electrode. Okay, this is oxide, and these are the photographs obtained by the secondary ion mass spectroscopy, SIMS. They deposited the metal electrodes, LSMO electrodes here. It's like a mesh, and this is a gold electrodes deposited on top of the oxide. I think the oxide is extremely stabilized 0 point. Okay, and applied electric field to these electrodes for a while, and then remove the electrodes, and then check the concentration of the oxygen 18. Okay. So this experiment was done in the atmosphere of oxygen 18, not the oxygen 16. So oxygen 18 can be detected by the SIMS. Okay. So in case of the LSMO, because this is the oxide electrodes, the oxygen can easily go into the LSMO electrodes. So you see under the mesh, the oxygen 18 can be detected almost all the part. And for the gold, it doesn't go into under the electrodes, but just here at the edge, the perimeter of the electrodes. So actually, all the chemical reaction that occurs at this boundary, or triple phase boundary, that is the boundary of the metal and the atmosphere and the oxide. So this point is important to understand the phenomena. And also, I'd like to say the chemical reaction occurs just at the interface, because we have changed the thickness of the oxide and how the reset and set voltage changes. But it doesn't change actually. This is because the electric field is applied only to the interface. It doesn't apply to inside the oxide. So if you change the thickness of the oxide, those voltage doesn't change. So the important part is, I think, in this picture I wrote, emphasized two interfaces, but I think the most important part is the top electrode, and the atmosphere is there. Okay, so the hysteresis curves can be classified into again the 4 types, further classified into 4 types here. Okay, this is a threshold switching, and this can be classified into symmetric one and asymmetric one. So symmetric, asymmetric means the rotational symmetry, not the mirror symmetry. Okay, so just the symmetric. So you can rotate 180, rotate, and it will become a similar one, same one. And this is called a non-polar. This is called a unipolar. So sometimes you will be confused by the word unipolar and non-polar, but unipolar is only for the asymmetric case because it doesn't show any change in one side, but it occurs only the positive side, or occurs only the negative side. But non-polar case, you can observe the switching in either the positive side and negative side. It doesn't depend on the polarity, so it's called a non-polar. So this is a bipolar. This is a bipolar. Okay. And for the ground switching case, okay. So the asymmetric one becomes like this, and the unipolar one becomes like this, and bipolar symmetric one becomes like this, and these are called NDR, but it's not necessary to be the real NDR. Okay? And the branch type without NDR is like this. So, but these three, you can't see any reset switching or set switching. So once it becomes in this case, once it becomes a low resistance state, it cannot. It can be back to the low resistance, high resistance state. So this cannot be useful for the random access memory. So this is only useful for the ROM degree. Okay. So these are also not useful for the random access memory. So we omit this. And also we can't really see any good examples for this one. So we don't. I don't mention for these at this moment, and I can't write the good picture for these. So I like to say the old histories you can see in the literature, in many reports, but those are classified into these 5 types. Okay. And I did this kind of classification 6 years ago in some conference, and I showed this kind of classification, but I was pointed out, and I said these are caused by the chemical reaction and so on, or maybe more transition and said, but people pointed out, that's okay, but you can't explain these 2 types. Okay? So I'd like to explain from now on why we can explain these 3 types by the chemical reaction, but it cannot be explained by these 2 types cannot be explained by the chemical reactions, but actually these 2 cannot be explained. So at first I didn't know the word Memristor, but after 3 years or 4 years later, after my classification, I was so surprised to read the paper in Nature. The HP guys reported Memristor, and that is actually hit to this kind of hysteresis. Okay, I will explain from now on. Okay, so first of all, I'd like to say this kind of hysteresis first. So, in order to understand the chemical reactions, I'd like to explain something about the defects chemistry. I'm a physicist, I'm not a chemist. So when I first read the textbooks of the defects chemistry, I was so confused because I don't understand all these complicated chemical equations and all these familiar marks. And maybe some of you are not familiar with this. I'd like to explain that briefly. So this one is the oxygen vacancy, and 2 dots means 2 plus. I don't know why they use these symbols. But E dash means E minus. This is electron. So this one is a metal in metal site. Metal in metal site. So this means metal in metal sites is minus charge. So this means metal in metal site without charge plus 1 electron. And this is the oxygen in oxygen site without charge. And this is oxygen gas in atmosphere. Or it can be provided from some materials surrounding the oxide of the resistor around. So depending on the difference of the redox potential, the oxygen can be provided from other materials to the interesting materials. Okay. So this one is metal vacancies, and so on. This one is intercalation of oxygen, and this is intercalation of interstitial metal, interstitial oxygen. Okay, so as you clearly see here, almost all the materials can be classified into N-type defects or P-type defects. Okay. So, but you want to say something because the titanium oxide, many people discuss about the oxygen vacancy. It shouldn't be interstitial metal, interstitial titanium in this case. So, but these two are not severely distinguished. Okay? So in some temperature, it is easy to consider the interstitial type metal in these materials, but it can be also understood as a oxygen vacancy. So these two are just a family, so you don't need to consider so much about the difference of these two. And these two are also the same. So what I want to say is N-type materials gives the electrons by and also the oxygen gas. So if the oxygen gas is adsorbed to the surface, the chemical balance shifts to left side, and the number of electrons decreases. So it becomes less conductive, okay, in those materials. But in this case, if you consider the absorption of the oxygen, like this, the chemical balance shifts this way, and so that increases the number of the holes. So the system becomes more conductive. So there's a clear difference of these two types. Okay? So the bipolar switching can be easily understand if you understand the chemical defects chemistry. Okay? So the N-type materials, if you dissolve the oxygen, so the oxygen will go away from the system. So the balance goes this way, so increase the electrons, so the system becomes more conductive, and the set transition occurs. Then, for the absorption of the oxygen, as I mentioned, that decreases the number of the electrons, so the system becomes less conductive, and the reset switching occurs. And then P-type, the opposite things can occur. So if you see the direction of the hysteresis curves, you can tell which type of materials is in your resistance switching samples. So this can be explained in many examples. So almost all the examples can be explained by this. Okay? So for this one, I said this is a rapid chemical reaction considered with branch type switching. Okay, because for the samples which show the threshold switching, there's also common features like this. So those samples, the off state, that is a high resistance state, the current is almost proportional to the size of the area of the top electrons, like this. But for the on state, that means a low resistance state. If you change the area of the samples, the current doesn't change so much, like this. So it means the current is restricted, concentrated on some small part compared with the area of the top electrons. So we call it the electric faucet model. So the initial stage is the back-to-back formation of the Schottky barriers like this, or it can be any kind of interface. But you know you need to apply the huge voltage at first. That is called the foaming. And after the foaming, the inside of the oxide changes like this. Or if you prefer the formation of filament, you see there's a lot of filament inside. if you prefer the domains, or you can see there's a lot of domains inside. Or if you prefer the breaking network model or something, or you can write a lot of breakers inside. So I don't mind anything. But the important thing is just at the here, there's a current constriction structures. That is important. Okay? And the forming makes the current constriction structures. So if the device is in the nanoscale, no forming is required, I say. Because this is, okay, so we just essentialize this structure like this. So this is a top electrode, and this is a bottom electrode. And the oxide is actually not so important. So it's just shrink to this size. Yeah? Okay? So this is oxidized titanium. And actually, we have prepared this kind of samples by spread the silicon oxide particles on top of the gold. And there's nanoholes a lot. And then we deposit the titanium on top of that. And the titanium is oxidized by getting the oxygen from silicon oxide. And then there's this titanium oxide there. And we deposit the top electrodes this, and then we measure the resistance switching, and then without electric forming, it shows the resistance switching. So because we have already prepared the current constriction structure from the first, you don't need to do the electric forming. So from the beginning, it shows the resistance switching. And it shows a very good resistance switching. Okay? So, now I understand. So these are caused by the chemical reactions. And this is a slow chemical reaction. This is a rapid chemical reaction caused by the current constriction structures. So this is because this is slow because of most of the epitaxial samples shows this kind of branch type switching. So the current doesn't constrict, so the temperature is low. But how can we understand this type of switching? So that's easy because now we know that those are caused by chemical reactions, and there's two types of bipolar switching, M-type and P-type. Then we can combine these two. Okay? So, but just remember, reset switching occurs for the high current. Okay? Reset switching occurs for the high current state. So that means the temperature is high. So we just combine these two. For this is reset switching as a parameter. That if the alpha is large, which means the temperature is large, or the current is large, and then combine these two equations, then you get this complicated chemical reactions. It looks quite complicated, okay. But if you really see these chemical reactions, but it's not really complicated, okay? So because it's clear, okay? So by the dissolution of the oxygen, and if the temperature is high, I mean high current, the reset reaction occurs. Okay? And if the temperature is low, the set reaction occurs. Okay? So the vice versa occurs here. So this can be understood by the chemical reaction, but you may have a question. Why you need to consider the two types of defects? So, but remember, in your samples, not your samples, our samples, you just remember all the samples which shows a non-polar resistance switching, you use the different types of metal electrode and oxide. I mean, for example, the cobalt oxide is a P-type. Okay? If you put the tantalum oxide on top of the cobalt oxide, the tantalum forms the tantalum oxide that is N-type. So there's a mixture of the N-type effects, I mean the oxygen vacancy for the tantalum oxide, and also the cobalt interstitium in the cobalt oxide. Okay, so there's a mixture of the cobalt oxide and tantalum oxide at the interface. Then you realize a non-polar resistance. But if you put the platinum electrode on top of the cobalt oxide instead of tantalum, your switching becomes bipolar. Okay? So even for the cobalt, the same cobalt oxide, depending on the kind of the metal electrodes, or depending on the kind of the p-type or n-type, you can realize the non-polar and the bipolar easily. So that is also the evidence of the chemical reaction. So you may ask why the platinum nickel oxide is non-polar. So the nickel oxide is a p-type. And what is platinum? But if you deposit the platinum by the sputtering, then this is a report of oxide on the platinum is sputtered on top of the nickel oxide. And then the nickel oxide is, forms another kind of oxide, that is a nickel 203. That is N-type. So there's a mixture of the P-type nickel oxide and N-type nickel oxide. So that causes differences. And also, you may have another question: why sometimes the platinum oxide shows non-polar behaviors? But if you deposit the platinum on top of the titanium oxide without care, I mean sometimes the interface heats up, or you can deposit by a very large kinetic energies. The platinum forms a platinum oxide on top of the titanium oxide. Then the platinum oxide is N-type, and the P-type, and the titanium oxide is N-type. So there's a mixture of these two. So the non-polar switching realized. So as you know, if you prepare the interface carefully, the platinum titanium oxide by epitaxial way, that only shows a bipolar resistance. And also, for the case of platinum nickel oxide, there's recent reports, several reports. If you prepare the epitaxial platinum nickel oxide, platinum electrodes and the nickel oxide, that only shows a bipolar switching. So that also underpins my predictions. And also, this can be confirmed by another thing that is called the Wagner-Hoffe theory. I don't have any good pronunciations, but if you dope some kind of ions into those defect materials, you can control the speed of the reduction of oxidation. So, for example, this is a metal deficient oxide, nickel oxide. If you dope the lithium to the nickel oxide, the number of holes increases, but instead the nickel vacancy decreases, so your oxidation speed decreases. So if you dope lithium to the nickel oxide, you can realize a high-speed reset. Okay? But if you dope the titanium 4+ instead, your number of holes decreases, so the system becomes less conductive, but the nickel vacancy increases, so your oxidation speed increases. So actually, this has been confirmed by several groups. This is the data from Samsung. This is the data from Japanese groups. This is Fujitsu. Sorry for that. But they said if you dope the titanium into the nickel oxide, the switching speed increases drastically. This is 10 nanosecond for reset. This is 5 nanosecond for reset. So that is clear indication of these caused by the chemical reactions. Okay, so I don't have enough time, but I just mentioned about the memories. Okay, this is just a short, several minutes. Okay, so these two cannot be understood by those chemical reaction models because it is easy to understand if you write the direction of the, okay, like this. So for the chemical reactions, so this state is stable, but if you reach to the point, it changes to another state by the chemical reaction. And this state is stable, but if you reach to this point, it goes back to another point. So that is a chemical reaction. But these types of behaviors are different. So, okay, so this one is okay, but follow this red line, you reach to this point, but nothing occurs. We can understand by the chemical reaction, by this no action. Okay? So you goes to this point, and if you comes back to this point, then the switching occurs. Okay? So I didn't have any knowledge on the Memristor 5 years ago. So I was pointed out many researchers in the conference, so I gave up to explain this at first. But now I know this can be explained by Memristor, so I should have gotten an idea earlier. But anyway, this is different from the chemical reactions. Okay, so only a few reports in the literature, as you know, there's only a few reports on this type of hysteresis. Okay, so this is I call it Memristor type hysteresis, and actually we have observed this kind of hysteresis only one time in our STO samples. Okay, so this is a Memristor type behaviors, and Hewlett-Packard people reported in their papers. So this first, when you go back to this way, so you can see transitions. Okay, and this can be explained in a very clever way. I didn't have any idea at that time. I really regret. Okay, so just rotate this one to this way to compare with this paper. Easy. So you see this one goes to this way and goes back. Okay, this goes back this way. This can be caused by the delay of the current change compared with the change of the voltage. Okay, so your voltage changes this way, but you assume the migration of the oxygen inside or migration of some kind of defect inside samples. So the migration doesn't follow the voltage change exactly. So there's a time delay. So the current delays follow the change of the voltage. So that will make this kind of shape of the IV curves. So this is the conclusion of my talk. Okay. So I said these types of hysteresis can be explained by the somehow the chemical reactions at the top of the electrons. Okay, and these two cannot be explained by the chemical reaction because these are caused by the change, caused by the migration inside the samples. So actually, we have recently prepared the titanium oxide samples, and if we do the hard electroforming, so we always observe this kind of resistance switching hysteresis, but if our forming is soft enough, so it doesn't create a real structure, electrode. In that case, sometimes we observe this kind of hysteresis. So I think we can compare hysteresis, this kind of hysteresis by the strength of the electrode forming. But I'm not quite sure, but that is current research going on. Okay. Thank you very much.
The session is now open for questions.
just to clarify for myself, you say you identified several types of switching, which are chemical reaction, and then you wrote down this effect reaction. And does that involve that actually you have a triple junction and you reduce the oxygen content in the sample? So if you like form more oxygen, you lose oxygen, you form more oxygen vacancy in your material, and you lose oxygen to the ambient.
Yeah.
And so if you would passivate your sample.
Yes, that's a good question. So in some samples, if we passivate by using some materials on top of our resistive switching samples, the resistive switching does work.
Okay.
But the tricky thing is, if we use a platinum electrode, the platinum can contain, it's my guess, but the platinum can contain some amount of oxygen inside. That is known in the previous tables. So in that case, if we passivate the samples from the atmosphere, but still the chemical reaction occurs. I think that is caused by the contained oxygen inside the reaction.
You were right at the end. I would be happy if you return to this last Memristor phenomena and explain once again the importance of the time delay. That seems to be crucial evidence for you that this is an ion migration related thing. So what happens when you speak faster, slower? How is this an evidence?
But you should ask the question to the HB guys. Because I didn't do this kind of experiment. But I don't know what happens if you change the scanning speed. Sorry. But I'm also interested. Yeah, your turn.
Okay, so again, we will hold for a break.
That was a good one. Check that into the key in there. Instead of standing the same way, proportionally look through the just grows, right? Break over? Oh, I hit the stuff. Yes.